So hey guys, this is Dipesh, and in this particular video we will be starting with deep learning, and we'll see what is the main difference between deep learning and machine learning, and we'll also talk about neural networks and how neural networks work. So before we begin, just a quick note that you should have a basic knowledge about calculus, should have a basic knowledge of linear algebra and matrices. Okay, so more specifically, you should know how to do how you should know about derivatives, you should know about functions, and you should also know about matrix multiplications. Okay, if you don't know these maths topics, don't worry. What you can do is you can watch the theory and you can directly skip to the implementation part. So let's get started. So what is deep learning? Now, just like I said in your in our first lecture, that artificial intelligence artificial intelligence is basically a result of machine learning and deep learning. Okay, and deep learning is a subset of machine learning. Okay, the main difference between machine learning and deep learning are the types of algorithms or the types of models that are used. Okay, in deep learning, we specifically use a special class of models called as neural networks. Okay, whereas in machine learning we use models which have different architectures and which are based on various statistical methods. Okay, so just keep this in mind. The major difference between machine learning and deep learning is that in deep learning mainly use neural networks, and machine learning is basically a generalized statement. Okay, machine learning basically consists of many different areas, and deep learning is basically one part of machine learning. Also, I said in our first lecture, I said that there are three types of machine learning: supervised machine learning, unsupervised machine learning, and reinforcement learning. The neural networks that we use in deep learning are a part of supervised machine learning. Okay, so the data that we'll use to train a neural network is labeled data. Now let's see what a neural network is. Okay, now the neural networks that we use in deep learning are highly inspired by the biological neural network inside a human body. Okay, so first I will give you a quick analogy of what the biological neural what a neural network is, and how the neural network functions inside a human body, and then we will look into the deep learning neural networks. Okay, so the design of neural networks is inspired by the biological neural networks composed of biological neurons. So now inside our brains, inside the brains of all the inside the brains of all the animals, what we have is we have something called as a neural network. Okay, and a neural network is composed of a large number of neurons. All right, so in our human body, the brain basically controls different parts of different body parts. Okay, and more specifically, this is done inside our nervous system. And inside our nervous system, what the nervous system does is it takes electrical signals from our brain and it sends those electrical signals to different parts of our body. Okay, by sending electrical signals through the nervous system, our brain basically helps us control different body parts. Now the way nervous system transmits electrical signals is through something called as neural network. Okay, and a neural network is nothing but a uh, a structure which is made combination of a large number of neurons. Okay, so in neuron individually a neuron is very simple. Okay, what a neuron does is it takes a electrical signal and it outputs another electrical signal. Okay, so more specifically, let's say our brain sends some electrical signal, then a neuron will get that electrical signal as input. It will do some processing on that electrical signal, and then it will output that electrical signal. Okay, now again, all the neurons in a neural network are connected to each other. So you can in this image you are looking at two different neurons. Okay, you are looking at two different neurons. Now both these neurons are connected to each other. Okay. So when a neuron takes a electrical signal as an input, what it does is it does some processing and it outputs that electrical signal. Now that electrical signal is again sent to another neuron which is connected to this neuron. Okay. So in this similar fashion, there are hundreds of billions of neurons inside our body. Okay, there are billions of neurons in our body connected together to form the neural network. And in a similar fashion, what happens is, the electrical signals that the brain sends, it basically goes through each and every neuron, and at the end of the neural network, we get another final electrical signal which is then sent to different body parts. Okay. So just try to understand the analogy here, just try to understand the architecture that is going on here. So a neuron takes the input, gives the output, and sends this output to another neuron, and and now this new neuron does the same thing. And like this, there are hundreds of billions of neurons in our body which together form a neural network. Okay. Now again, individually these neurons are very simple. All they do is take some input, produce some output. Okay. But if you put together hundreds of billions of them, then they are able to do some very complex computation. Okay. So one analogy would be an ant hill. So an ant basically is very small. Okay. Individually an ant cannot do much, can do much thing. Okay. But if you bring out, let's say 2 or 3 million ants, then they together can build an ant hill. Okay. It's the same thing with neural networks. Individually a neuron, each neuron does a very simple thing, but if you bring about billions of them, then they can do some very complex things. Now since I told you that the neural networks that are used in deep learning are inspired by biological neural networks, the neural network that we use in deep learning is called as artificial neural network. Okay. Artificial meaning it's man created. Okay. So let's now see how a artificial neural network or the neural network that we use in deep learning works. Okay. Now also another name for artificial neural network is multi-layer perceptron. Okay, let me just write this. Another name for this is multi-layer perceptron or MLP. Okay. So whenever you hear the word multi-layer perceptron or MLP, just think of it as the most basic type of artificial neural network that you can create. Okay. So as you can see here, this is basically how a artificial neural network looks. Okay. So you can see that there are multiple number of neurons in our neural network. Okay. Just like the neural network in biology, there are multiple different there are a large number of neurons that we put together. Okay. So in a artificial neural network, what we do is we create different layers of neurons. Okay. So here you can see this is one layer, this is another layer, this is another layer. Okay. So in an artificial neural network, what we do is we take large number of neurons and we create we create different layers of them. Okay. Now going forward, we'll discuss how each neuron works and what are the functionalities of each layer. Okay. So don't worry about it. Just try to wrap your mind around this architecture. Okay. Because as a beginner it would be very hard it is very hard to understand this stuff. Okay, and until and unless you watch this video 2 or 3 times and implement this thing on your own, it is very difficult to get this thing. So again, I will repeat this. A neural network is a collection of neurons, and a artificial neural network or a multi-layer perceptron is basically a collection of layers where each layer consists of a large number of neurons. Okay, this neuron is also called as node. Okay, so just try to remember it. This neuron is also called as node. Okay, so whenever we talk about artificial neural network, we don't use neuron to define the to define this part of the neural network. We use the word node. Okay, because neuron is more related to biology uh, than deep learning. Okay, so whenever I'm talking about node, just remember that I'm talking about a single neuron in a artificial neural network. Okay, now the architecture that I told you about, this architecture, this is basically a very oversimplified version of the biological neural network. Okay, so human brain consists of 100 billion neurons arranged in a huge neural networks, but artificial neural networks don't mostly don't have 100 billion neurons, okay, or 100 billion nodes. We have only couple hundred or couple thousand nodes in an artificial neural network. So keep that thing in mind. All right, so basically just like aeroplanes, you know, just like aeroplanes were inspired by birds, they don't fly their wings just like bird. Okay, so if you have read history, you would know that the aeroplanes, okay, the aeroplanes were highly inspired by birds, but the aeroplanes that we see today don't you flap their wings just like birds do. All right, so in a similar way, the artificial neural network is basically a very oversimplified version of the biological neural network. Okay, so keep this in mind that the architecture, okay, the architecture is highly inspired by the biological neural network. All right, so now let's see why do we need deep learning, like why do we use neural networks. So mainly there are two reasons. Okay, first is the amount of data, and the second is the type of data. So now in situations there are situations where we need to create models using very large amount of data. Okay, so there are problems for which we need to train models with a large amount of data. Now in machine learning, the models that we use are very simple as compared to the deep learning. Okay, so the deep learning or the neural networks are very good at learning from large amount of data. Okay, and the models that we use in machine learning are very light and not that complex. Okay, now they are good for small data when you have small amount of data and you want to learn from that data. But if you want to learn from a very large amount of data, for let's say you want to learn from 100 let's say you want to learn patterns from 100 million images. Now 100 million images is a pretty big amount of data. For this kind of data we use neural networks. Okay, the next thing is the type of data. Now machine learning models are not good at dealing with unstructured data, whereas neural networks, the deep learning models are very good at handling unstructured data. So for example, let's say you want to let's say you want to classify images. Okay, now in order to classify images, it is very hard to create a machine learning model that will give us good accuracy. But in deep learning, using neural networks, we can very easily classify images. Okay, so keep these two things in mind, that when you have large amount of data, it is neural networks do very good job, or train very or give train very clearly or learn very useful patterns, and give very good performance from that data. Okay, whereas if when you have very small amount of data, machine learning models are fine. Now the second point is the type of data. The neural networks are very good at unstructured data, whereas normal traditional machine learning models are not good at dealing with unstructured data. Right? Now one disadvantage of neural networks, okay, one disadvantage of neural networks is that they are very hard to train and they need more computation power. Okay, whereas traditional machine learning models are very easy to train. Okay, they require very less computational power. Now if you in our previous lectures, what we did, we tried to train traditional machine learning models like linear regression or logistic regression on a local machine. Okay, now training these models on a local machine is fine, since these models are not that complicated, they are very simple. But if you want to train a neural network, you would at least need a very good GPU. Okay, so you cannot train, so it is very difficult to train neural network on your local machine unless you have a very good hardware. Okay, so in order to deal with this problem, we also have many other tools. So we can directly train a neural network on cloud. Okay, so we'll discuss these things at the end of this video. So right now just focus on understanding the neural networks. Okay, so don't worry, even if you don't have any even if you don't have any GPU, or you don't have any great computer, don't worry, at the end of this video I will share a tool with you, and you can easily train your neural networks on the cloud. Alright, now the next is types of neural networks. So just like we have different types of machine learning to solve different types of problems, we have different types of neural networks to solve different types of problems. Okay, each type of neural network is basically specialized to solve a specific type of problem. All right, so the artificial neural network, okay, the artificial neural network that we discussed here, this artificial neural network, this network is basically specialized to solve classification and regression problem. All right, and in this video we'll discuss about this particular type of neural network. All right, now there are also two other types of neural networks. One is convolutional neural network and the other one is recurrent neural network. The convolutional neural network is basically used for computer vision tasks. So whenever you want to do, let's say, object detection or image classification, convolutional neural networks are basically specially made for computer vision tasks. Now recurrent neural networks are used for something called as natural language processing. So natural language processing includes things like machine translation or sentiment analysis, something like that. So whenever you have text data, okay, whenever you have sequential data, for that type of data we use something called as recurrent neural network. We'll discuss about each and every neural network, and we also code them in Python in our upcoming videos. Okay, so don't worry about them. In this video we'll specifically focus on understanding artificial neural network or multi-layer perceptron. Okay, and in our next video what we'll do is we'll try to implement a artificial neural network using Keras library. All right, so next what we'll do is we'll understand how does a artificial neural network work. Okay, now up until now I think it should be very clear that the architecture should be very clear to you. We have different layers and each layer has a set of neurons, okay, or nodes, and yeah, so this is basically the architecture here. Okay, this is the architecture of a multi-layer perceptron, and as I told you earlier, a neural network, okay, is composed of different layers, and each layer consists of a set of neurons, okay, a set of neurons or nodes. Now there are mainly three types of layers. First is input layer, other one is hidden layer, and there is output layer. Okay, the hidden layer is always in between of input layer and output layer. Okay, now each layer basically does performs a different task here. Okay, each layer basically performs different task here. So input layer basically is responsible for taking the input, and output layer is basically responsible for giving the output, whereas hidden layer basically tries to learn the parameters. The all the necessary learning thing happens inside the neural, inside the hidden layer. All right, let me clear this. Okay, so the next thing is, remember that each and every neuron in a at any particular location is basically connected to all the other neurons in the next layer. Okay, so for example, here you saw that this one neuron in the input layer is connected to all the other neurons in the next layer. Okay, so this is same, this happens, this is same for all the neurons, okay. So even in the hidden, even in the even if you pick a particular neuron in a hidden layer, you will see that it is basically connected to all the other neurons. So here, since we have one neuron, any neuron, all the neurons in the hidden layer are connecting to this particular neuron. Okay, so let me give you an example here. So you can see that this is the first layer, and each neuron will be connected to all the other neurons in its next layer. And in a similar way, if you choose this neuron will again be connected to all the other neurons in the forward layer. Alright, let me clear this. Okay, so again we have a neural network which is composed of different layers, and each layer consists of a set of neurons or nodes, and each node at any particular point is connected to all the other node in its next layer. All right. Also, one very important thing is that there is no definite number of there is no definite or fixed number of nodes that you can have in each layer. Okay, depending upon the problem, you can have as many neurons as you want. Okay, so there is the number of nodes in each layer can vary depending upon your problem you are trying to solve. Okay, so remember this. So for example, if you are trying to, let's say, do binary classification, then in that particular situation you will have only one output which gives you the probability value. Okay, so the number of neurons in each layer can vary. There is no fixed number for neurons in a neural network. Let me give you some examples here. So if you look here in this video, what we are trying to do here is we are trying to classify, we are doing a binary classification whether the image is a dog or a cat. Okay, so you can see that the at the end we have only one neuron here. Okay, at the end we have only one neuron which is giving the output as dog or cat. Let me give you a good example of a regression problem. All right, so here let's say that given population, area and mortality rate of a country, we want to predict the GDP of that country, and we also want to predict the literacy rate of that country. Okay, now in this situation, since we have three independent variables, then in this situation, since we have three independent variables, we are having three nodes in our input layer. Okay, and also at the output layer, since we are having two dependent variables. Okay, we are trying to predict two different things here. We are having two neurons here. So depending upon your problem, the number of the number of neurons in each layer varies. Okay, so the number of neurons in the input layer will always be equal to your independent variables, and the number of neurons in your output layer will always be dependent upon your target variables. Okay, dependent upon your number of target variables. All right, so the input layer basically just keep this thing in mind that the input layer basically defines our input variables. So what happens here is our input layer is basically just our independent variables here. Okay, just our independent variable. So since we have three independent variables, so for example, let's say our population is 15 and area is, let's say, 10, and mortality rate is 11. Now what happens is we basically send this 15 to all the neurons. We send this 15 to all the neurons in the hidden layer. Okay, and in the similar way we send this 10 to all the other neurons in the hidden layer. So again, since at each neuron, at each point, the neuron is basically receiving multiple inputs here. So since we send 15 and 10, the neuron will receive 15 and 10. Okay, then it will do some processing, and again it will basically create an output, and then that output will again be sent to another neuron. Okay, which will again do some processing, and then it will output another value. Okay, so remember, the input layer basically defines our independent variables. All right, let me clear this. The main processing, okay, the main learning basically happens in the hidden layer. So hidden layer is basically very important. Also, one thing to remember is that we can have multiple hidden layers in a neural network. Okay, in this case, in this architecture, we are having only one hidden layer, but in real life cases you can have multiple multiple hidden layers, but the number of input layer is only one, and the number of output layer is only one. Okay, so keep this in mind, that we can have multiple hidden layers, but we can have only one input layer and one output layer. This architecture is more specifically called as multi-layer perceptron. Okay, so a multi-layer perceptron is a neural network architecture which has one input layer, one hidden layer, and one output layer. Okay, so this architecture is basically called as multi-layer perceptron. So the architecture that I showed you previously, let me just show you. Let me just see. This is not a multi-layer perceptron. Okay, this is not a multi-layer perceptron because we are having two hidden layers here. Okay, we are having two hidden layers here. Okay, so multi-layer perceptron is basically the most basic type of neural network, the most basic type of artificial neural network. Now this is an example of a deep neural network, since we are having multiple hidden layers here. Okay, multiple hidden layers, but we have only one input layer and one output layer. Okay, so this architecture is called as deep neural network. Okay, so you can see the resemblance between the name deep learning and deep neural network. So deep learning is basically, the name is inspired from this architecture. So we can have large number of hidden layers. So if you have, let's say you have 1 million independent variables, then then in order to learn from that data, you will have to create a very big neural network. Okay, so when you create multiple hidden layers, that architecture is called a deep neural network, which inspired the name deep learning. Okay, all right. So then again, as we discussed earlier, the hidden layer basically it represents our independent variables. It basically initializes the data. Okay, whereas the hidden layer is basically the main part where the learning happens, and the output layer is responsible for producing the output. Okay. Okay, so now we have an overview about the architecture. Okay, we know the components of the architecture. Now what we want to do is we want to see how each of these neuron work, each of these nodes work. So if you know how each of these nodes work, then we can easily understand how this entire neural network works. Okay, because each node does a very simple function. It takes an input, it does some processing with that input, and then it outputs another value, which is then again sent to all the other neurons. Okay, so what we'll do is we'll see what happens inside a single node. In the next video, what I will do is I will also show you a visualization. Okay, a good visualization of this neural network, so you get a more better understanding of the architecture. Okay, so one thing before we discuss the nodes is the learning parameters. Okay, the learning parameters in neural networks are what you call as weights. So if you have studied graph data structure, you know that in a graph data structure we have edges and nodes, and we can have a weighted graph data structure, or we can have a normal unweighted graph data structure. So if you have studied graph data structure, the concept of weight should be very clear to you. So the learning parameters in a neural network are the weights. Now each edge in a neural network, each connection that we see in a neural network has a weight connected to it. Okay, has a weight connected to it. Now just try to understand the architecture. Okay, as we go as we go more deeper into how a single node works, at that point it will be all crystal clear to you. But at this point, just focus on understanding the architecture. Okay, just try to understand the architecture and how the different components are connected. Okay, so now the weights. Okay, the weights are basically the edges, basically each connection. Okay, as I told you that each neuron is connected to all the other neurons in its next layer. Okay, now each connection is basically weighted, each connection has some weight. Now these weights are basically a number. Okay, now this weight can be anything. It can be 0.22, or it can be let's say 12.5 or something. These weights are basically real values. So again, here you can see in this diagram that each connection, okay, each connection is weighted. Each connection has a weight value, and these values are our learning parameters. When we train a neural network, our goal is to learn the most optimal values of weight. Okay, to learn the most optimal values of these weights that give us the highest accuracy. Okay, so again, each neuron is connected to all the other neurons in its next layer, and each such connection has a weight associated with it, and this weight value is nothing but a numerical value which we'll try to learn during training. Okay, so these weight values basically they keep changing during the training. Okay, and until and unless we find the most optimal weight values that give us the lowest loss and highest accuracy, we keep on training our neural network. All right, so now let's see how a single node works. Okay, it's very easy. I promise you, if you know even the basic of matrices and even the basic of calculus, it's understanding neural networks is very easy. the only hardest part in neural networks is understanding how the values are updated. Okay, as a beginner, you will don't try to get too deep into it. First try to get an overview, and then implement as many problems as you can using Python or any other language. And once you once you do a couple of projects or solve a couple of problems, then and then in that only after that you can be, I would recommend you to go more deeper into this concepts. Okay, as of now, just focus on how the output is created. Okay, just see how the output is created. Okay, so the node is basically the most basic component of a neural network, and we know that each neural network contains hundreds or thousands of nodes. Okay, now the function of node is very simple. It does two things. A node basically first calculates the weighted sum, all right, and then it basically passes that weighted value, that weighted sum, to an activation function. Okay, an activation function is basically a simple mathematical function. All right, a special type of mathematical function which we just, what we do is any node in the neural network, every node in the neural network does two things: calculate the weighted sum of its input and pass that weighted sum to the activation function. And then the value that we get from the activation function, that is the output of a single node. Okay, so here you can see x1, x2 and x3. X3 are the independent variable. These are basically our input values. W1, W2, W3 are weights. Okay, you can see each connection is weighted here. So so what we do is we send this independent variable values to this neuron, and this neuron does some processing. Okay, it does some processing and it creates an output. Okay, let me repeat this again. We have the we also remember that in order to create this output, we also use the weights. Okay, so let me repeat this again. A node basically does two things. It calculates the weighted sum, and then it passes the weighted sum to the activation function to produce the output. Now the weighted sum is nothing but the basically it is the it is the total sum of the product of each and every input and each and every weight. Okay, so for example, as we go forward, I will tell you how we calculate the weighted sum. As of now, just keep this in mind that each node basically receives multiple inputs. Okay, it calculates the weighted sum and it passes the weighted sum to an activation function and it produces the output. Okay, and in order to calculate the weighted sum, we also use the weights. Okay, so here you can see we have two inputs, we have their outputs. We have two inputs, we also have their weights. Then what we do is we calculate a weighted sum and we pass the weighted sum value to a function, and that function basically creates the output. All right, okay, so let's see how to calculate the weighted sum. Now it is very easy. Okay, so imagine that these are the input values. Okay, these are the input values and these are the weight values. Okay, these are the weight values. So now what happens is we basically first take the product of each input and each weight. Okay, we calculate the product of each input and we calculate the product of each input with their weight. Okay, and at the end we just add them up. So here you can see this basically represents a single node. Okay, So here you can see that since what we do is we first multiply 10 and then we multiply its weight 5.6. So here you can see we are multiplying 10 with 5.6, and again we are doing the same thing. We are taking the input and multiplying with its weight value. So 15 multiplied by 7.8, and again for all, we do this thing for all the inputs. Okay, we do this thing for all the inputs and we just add them up. At the end we take a sum of this value. So here since we have three inputs, you can see three multiplications here. So at the end the weighted sum value that we get is 294. Okay, so 294 is our weighted sum. Now what we do is we pass this 297 to an activation function. Okay, so we pass this 294 value to activation function, and this activation function produces another output value produces another output value, which is then the output of the node itself. Okay, so again we calculated the weighted sum, we pass the weighted sum to the activation function, and that activation function is the output of this node. So this is what happens in all the nodes in the neural network. So let me just show you. So in all these nodes, you know, so in all these nodes, the same thing happens. Okay, the same thing happens. We have an input. We calculate the weighted sum and we pass it to the activation function. The activation function outputs a value, and that value is the output of the node, and the output of the node is then again sent to all the other nodes in the next layer. Okay, so to all the neurons. So this is how one single neuron works. Okay, now what is activation function? So activation function is a special type of function which basically transforms an output from a node from nodes. It basically transforms the output of the nodes. Okay, it defines how the weighted sum is transformed into an output from a node or nodes in layer of network. Alright, now activation function, so there are basically many different types of activation functions, and depending upon the problem that you are solving, okay, you will use different activation function. So here let's assume we are trying to solve a binary classification problem here. So the activation function that I use here was sigmoid. So if you give 294 to a sigmoid function, it will give you 0.00172. Okay, sigmoid is the same function that we use in logistic regression. Okay, so there are various types of activation functions, and we use different type of activation function depending upon our problem. Also, remember a quick note that you can have different activation function in each layer depending upon the type of problem that you are solving. Okay, so what you can do is, so for each layer you can have different activation functions. So for example you can have, let's say you can have ReLU here. You can have ReLU activation in one layer, and you can have let's say sigmoid activation function. Okay, so there you can use different types of activation functions in different layers. Okay, now here again, like since for example here, now here since I was doing a binary classification, I was finding out if the image is a cat or a dog. Since I want a probability value here in the last output layer, what I will do is I will use sigmoid activation function. Okay, so sigmoid activation function will give me a probability value between 0 and 1. So depending upon the type, type and the problem that you are trying to solve, you'll use different type of activation functions in each layer. All right. Okay. So also remember that activation function is only present in the hidden layer and the output layer. Okay, activation function is present only in the hidden layer and output layer, because the input layer basically represents our input data. So here we have three independent variables. Then we don't do the weighted sum and activation function here in the input layer neurons. Okay, what we do is we directly send these values. We directly send the independent variable values to the hidden layer. So let's say population is 15. Okay, then what we'll do is send 15 to all the other neurons in the hidden layer. So in that way, remember, activation function is only used in hidden layer and output layer. Okay, and the type of activation function that you use in your output layer is very important, because depending upon your problem, you will use different activation function. Okay, if you're for example, if you're using binary if you're doing, let's say, binary classification, then you will use only one node. You'll use only one node, and you'll use sigmoid activation function. But let's say you are doing multi-class classification. Okay, you are trying to classify multiple things, so you will have, so depending upon your number of classes, you will have multiple neurons in your output layer. So if you have, let's say, 3 classes you want to predict, then you will have 3 neurons, and each neuron will basically give a probability. Okay, each neuron will basically give a probability value, and each neuron will represent a different class. Okay, so now this is how a neural network works. Okay, there is no fixed size of or fixed architecture of a neural network. Depending upon your problem, you use different architectures. Okay, so this is how the output of a neural network is calculated. You have the input layer where you have your input data, input variables, and each neuron basically just does two things: calculates a weighted sum, and sends the weighted sum to the activation function. And the same thing basically happens until the last layer, which is the output layer. And at the output layer, we again have again we take the uh, uh, weighted sum, and we have the activation function, which in then basically produces the final output of the neural network. Okay, so I think by now you should be having a pretty good understanding of why I said that traditional machine learning models are uh, very simple as compared to neural networks. Also, don't forget that the learning parameters. Okay, the reason why we are training a neural network is to learn the most optimal values, or learn the most optimal values for the weights. Okay, now we have a pretty good understanding of the architecture of the neural network and how it produces a output. Now let's see how we train a neural network. Okay, now I won't basically tell you how the entire process, or how the entire gradient descent works. Okay, because by now you should have a pretty good understanding of how gradient descent works, because no matter what model you're using, if you're using linear regression or a neural network, okay, in almost all cases we use gradient descent. So by now you should have at least a basic understanding of gradient descent. So now again, like the fundamental pattern, or the fundamental steps for training a neural network are same as we same steps that we took in order to train any other machine learning model. So basically what you can do is you can think of a machine learning model or neural network model as a function of its input. We have some input. We have this model with different architecture, and what we do is we train this model. So again, we have some input, we have some model. Okay, the model, basically we give this inputs to our model. The model produces the output, and then we calculate a cost function. All right, then we calculate a cost function, and depending upon the value of the cost function, we basically try to update the parameters of the model. Okay, this is true for almost all the machine learning models. Okay, all the machine learning models and deep learning models. So basically you can think of, no matter what algorithm or no matter what model you are using, you can think of it, think of each model as a function. Okay, as a function of its input. And the idea, the steps to train this function or this model are same in most cases. Okay, we try to minimize the loss function, and we try to iterate, or we try to iterate our data and try to update the parameters. Okay, so I won't tell you how the entire details about gradient descent. Okay, I will give you a pretty good overview about what is happening here. So what we're trying to do here is we're trying to minimize our cost. Okay, we're trying to minimize our cost, just like any other machine learning model. Even in neural networks, we're trying to learn the weight values. Okay, weight values. So, and this formula that you see, this is the same updation formula that we use in machine learning. Okay, so in all the machine learning and deep learning world, this formula is basically used to update the weights. Okay, update the weights such that until we reach the most optimal weight values. Okay, and I've also discussed this very clearly in our linear regression video. So just remember that this formula is designed to update weights in such a way that we get the lowest value for our cost function. Okay, now what I will do is I will explain you how this formula actually works. Okay, I'll explain to you why does this formula work. Alright, so the formula is very simple. You have a weight. Okay, you have your weight. So this value, this wx, okay, this value basically represents the new updated weight. Okay, and this value for wx represents the old weight. Okay, again remember, this is the old weight. Okay, this is the old weight and this is the new weight. Now the formula is very simple. What you do is the formula is basically old weight minus the product of learning rate and the derivative of or the partial derivative of the cost function or the error with respect to the parameter w. Okay, so let me repeat this again. The formula to update this weight is w minus learning rate into partial derivative of the cost function with respect to this parameter itself. Okay, now forget about learning rate. Okay, because learning rate is a constant, so we don't have to worry about it. Now I will explain to you why this formula works and how our weights get updated. So now let's say at the start of the training, now let's consider this graph. Okay, we have our cost at y-axis, and we have our w parameter which we are trying to learn by training. Okay, now at this point At this point, basically, when you're trying to train your neural network, okay, at the first iteration, okay, at the first iteration, our cost would be very high because our neural network has not yet learned to solve the problem, okay, and we have not updated any weight values yet, okay. So at the first few iterations, the cost function will be very high. But now let's say what happens is, let's say you are at this point, okay, at third or fourth iteration. Let's say you are at this point. Let's say you are at this point, okay, at this point. Now if you take a derivative at this point, okay, if you take a derivative or slope at this point, it you will get a negative value, okay, you will get a negative derivative, okay. Now imagine this, we want to update the value of w, okay, and at this point we have, if we take the derivative, we get a negative value for the derivative. So if you look at the formula, now again, if you take the in the formula, what we take is, we take the derivative of w. Now we know that at this point the cost is very high. Now since the cost is very high, what we want to do is, we want to reach at this point, right? We want to reach at this point. That is the lower, that is the value where the cost function is, cost is very low, okay, where the cost is the global minima, okay, the global minima, we are trying to reach a global minima here. So we want to drive our cost here, which also means that we want to change the value of our w. We basically, which also means that we want to increase our value of w, okay. We want our at the start of the training, our value would be somewhere here, you know, our value would be somewhere close to 0, okay, the value of our weight, okay, the value of our weight. But as the as we train our model, what we want to do is, we want to reach this point. That is, we want the value of w at this point, we want the value of weight at this point, which will give us the lowest cost value, okay. So we want to basically change the value of, update the weight of value of our w, or the weight, in such a way that it gives us the lowest cost function, okay. Now here, at this point, at the start of the training, our slope is our cost is very high. So if you take the slope, okay, you take the derivative of the cost function with respect to this w, then you will get a negative slope, okay, negative slope. Now our aim is to basically update the value of w to go towards the positive axis, okay. So basically we want to increase the value of w. So since our derivative is negative, what happens is, since our derivative is negative, and our formula already comes with a negative sign, these two negative signs cancel each other out, okay, these two negative signs cancel each other out, okay, these two negative signs cancel each other out, and what we get is the sum. We basically add, we basically get the sum of, we basically take the sum of old value and then derivative. Now this basically increases the value of w, which means that it shifts the value of w towards the positive x axis, where our global minima lies, okay. Now again, if you take again another derivative, okay, then again we will get a negative slope, right, negative slope. Then again, since our formula already comes with a predefined negative sign, if we try to calculate this value, okay, if you try to do, let's say, -5, okay, -5, if you try to calculate this, what we'll do is, we'll do wx plus 5. So these values will cancel each other out and the value of w will increase, and we will basically shift towards the global minima, okay. Now let's imagine, imagine this. Let's say you are here, okay, let's say you are somewhere here, your value of w is somewhere here, okay. Your previously our value of ws was on the opposite side. Okay, so we wanted to basically, in order to reach the global minimum, we wanted to increase the value of w. But now let's say your w value is somewhere here. Okay, somewhere here. And if you take the slope here, if you take the slope here if you take the slope here, you will get a positive slope here. Okay, you will get a positive derivative here. So now again, let's say our derivative is plus phi. Now what will happen here is our our weight will basically we will basically subtract the value of derivative. Now previously, since our derivative was negative, we basically cancelled the negative signs and we added the derivative to our weight value, which in turn increased our updated our it basically increased the value of our w. Now here what is happening is, since our derivative is positive, okay, since our derivative is positive, the the cancellation thing doesn't happen. Okay, and we basically subtract the derivative we subtract the derivative from the weight value. In short, we move towards, since we are here, we move towards the global minima. Okay, we shift our weight value or w value towards the global minima. So this is how basically the formula works. It has been designed to update the weights in a such a way that that you reach this global minima. Okay, the minima where the cost function is the lowest. All right, we train our model or keep updating the weight values until our cost function doesn't change much. Okay, or it reaches close to zero. So this is how basically we do weight updation and training in neural network, and not only neural network but in general in almost all the machine learning models. Okay, we have this architecture. Let me just show you. Okay, so we have this architecture. Okay, this architecture basically produces this architecture basically takes input. Okay, it takes some input. It does all. Now each neuron basically takes input and produces some output, and it happens until the last layer, that is the output layer, and at the last layer we get some value. Okay, we compute the cost function, and we compute the derivative. Okay, now since here we want to update all these weight values, what happens is we calculate the derivative of all these weights with respect to the cost function. Okay, we calculate the derivative of all these weights with the cost function, and we update these weights using the updation formula, using this updation formula. Now in this diagram I have only shown you one single weight. Okay, but here we do the same thing with all the weights. Okay, we do the same thing with all the weights, and we do this until we get a desired output from the neural network. Okay, all right, so this is how a neural network learns. All right, the next thing that we will do is uh, we'll see the mathematics of neural network, like how we can represent this thing mathematically. Let me have some water. Okay, then we'll discuss it further. Okay, so in each neural network, so basically we saw that a neural network is nothing but just different layers, layers of inputs and weights. Okay, so now what we can do is we can represent this neural network. We can represent this neural network using matrices. Okay, using matrices. So for example, you see here, you see this. Now we can basically represent these three layers. That is the hidden layer, uh, input layer and output layer using matrices. Okay, so basically what happens is we we can represent each layer, okay, each layer as a matrix. Okay, and we can also calculate the weighted sum and output of these neurons using matrices. So let me explain this more clearly. So you can see in this neural network we have two inputs. Okay, so we have two input nodes. So now what we can do is we can represent this input as a column matrix. Okay, since we have two inputs, we can represent it using a 1 by 2 matrix. Okay, 1 by 2 column matrix, and we can represent the weights, okay, the weights between the input layer and the hidden layer using a single matrix, using a single matrix. So here you can see that since we have three nodes, we have three nodes and we have two input nodes, we can represent the weights between them using a 3 by 2 matrix. So each row of this matrix represents the weights of one neuron. So for example, this W11 and W21 are the weights of the first neuron in the hidden layer. You can see this. Yeah. So similarly, W13 and W23 are the weights of the last neuron in the hidden layer. Okay, so basically we can represent this entire thing, this entire operation, uh, by just a couple of matrices. Okay, so here you represent all the input values in a column matrix or a vector, and if you have n number of inputs, okay, here we have n is equal to 2, and if you have m number of nodes in your hidden layer, okay, since we have here three nodes in a hidden layer, so m is equal to 3, then all the weights can be represented in a m by n matrix, again, which is 3 by 2. As you can see, we have a 3 by 2 matrix to represent all these weights. Now calculating the weighted sum for each of these neuron. Okay, the calculating the weighted sum for each of these neuron in the hidden layer is just a matter of calculating the dot product or the multiplication of these two matrices. Okay, now let me repeat this again. Calculating the weighted sum of all the nodes in the hidden layer is just a matter of finding the dot product or simple multiplication of the input matrix and the weighted matrix. Okay, so this is how simple a neural network is. Okay, now our goal of neural network is to find this find the most optimal values of this matrix. Okay, to find the most optimal values of this matrix. All right, so here again we have the weight matrix and we have the input matrix. What we do is we take the dot product, and then when we calculate the dot product, we get another matrix. Now this matrix basically represents the weighted sum of all the output values of all the hidden nodes. Okay, this basically represents the weighted sum of all the nodes in the hidden layer. Okay, so for example, the first row basically represents the first row basically represents the weighted sum for the first node. The second row represents the weighted sum for the second node. Okay, so after computing their dot product, okay, after computing their dot product, we get another column matrix where each column matrix represents the weighted value of the nodes in the hidden layer. Now, in order to compute the output of each of this, in order to calculate the output of each of this node, what we do is we simply apply an activation function. Okay, so we have some function. Okay, and all we do is we just apply this function to all the to this matrix. Okay, so this after this we get another matrix. Okay, we get another matrix which is the output of this output of the hidden layer. Okay, output of the hidden layer. So this is how basically the uh, actual computation happens in a neural network. Okay, in the real world we don't create these dots and all. Okay, we simply just create matrices. Okay, we simply create matrices. So yeah, this is how a neural network works. Okay, in neural network, remember, a neural network is nothing but just a bunch of matrix calculation. Okay, and it's really wonderful how what all things we can do. Imagine like for example a object detector. Okay, now a object detector, as a human, when we see a model predict a image. Okay, predict an object. Now as a human we feel that it is the model that is basically detecting it. Basically there is a factor of consciousness attached to it, but in the back end we know that it is just a bunch of matrix calculation. Okay, it is just a bunch of numbers. So yeah, this is how a neural network works. Now let me introduce you some of the most used tools in deep learning. Okay, so some of the most used tools are TensorFlow, Keras, PyTorch, and Google Colab. So TensorFlow and PyTorch are the major Python library. Okay, are the major Python library that is used to create deep neural networks. Okay, so in whenever you will if you whenever you will be talking about deep learning, you'll definitely talk about TensorFlow or PyTorch. Okay, and Keras is basically an API of TensorFlow. So if you use TensorFlow just as it is very difficult to create neural networks. But Keras basically provides a high level abstraction layer over TensorFlow. So if you so basically Keras uses TensorFlow, but it is very easy to use Keras. Okay. So in this we in our next videos we will use Keras. Okay, because as a beginner Keras is very good. It's really simple and we can create a neural network in like 3 or 4 lines of Python code. Okay, so remember TensorFlow and PyTorch are the major libraries in deep learning, and Keras is basically an API library over TensorFlow. And Google Colab is again another major tool that is widely used in deep learning. Google Colab is basically a tool, Jupyter notebook like tool on which we can train our neural network. So as I said you earlier part that training a neural network requires a very large amount of computation power. You know, so so Google Colab solves that problem. It basically provides a Jupyter notebook like interface, and all we have to do is we just have to give it our data and write the code, and it will automatically handle all the training and all. Okay, so we don't have to worry about hardware or having any powerful GPU or stuff. Okay, so yeah, this was it, and in our next lecture we'll see how we can implement a neural network on Google Colab using Keras. Okay.